Hello everyone and welcome back to this exploration of vector calculus, and today we're going to be talking about several different important theorems that you definitely need to know when it comes to evaluating integrals in higher dimensions, both double or multiple integrals and also line integrals, both of scalar functions and vector fields as well. Let's just recap some of the things that you definitely need to know before we get into today's discussion. So, the first thing you definitely need to know is how to take line integrals of scalar functions. So let's assume that you have a function of two or potentially more variables, f of x, y, and let's assume you want to calculate the line integral of this function over some path c that's parametrized by some function u of t, where t ranges from a to b. Then all you have to do is find the magnitude of the associated velocity vector of u, that is the magnitude of u prime, multiply that by fxy, and then integrate with respect to t from a to b. And that's going to give you a particular number that measures, in some sense, the area under the curve or the one-dimensional surface along that path c. Another variation of line integrals is that of vector fields, which is sometimes abbreviated by f dot product with du. And keep in mind, a vector field is going to give you a vector for every single point in that particular domain. So that means f is going to be a vector, du will also be a vector, in particular x prime and y prime. And then that's going to give you the dot product between two vectors, which is going to be a scalar function. And then you can integrate that from a to b with respect to t, and that will give you the line integral of that vector field. So let's just draw a quick little diagram of what exactly these things are talking about, in case you have forgotten. So let's assume that we have some path C located here, and let's assume that it's parametrized in that direction. And let's assume that we have some function over that particular path. Let's assume that that's our path. Maybe it looks like a Gaussian or something like that. So this line integral is going to be calculating the area of that shaded purple region underneath that orange curve along that path on the plane C. And then integral of a vector field. Let's assume that we have some vector field, and let's draw some paths in this vector field. Let's assume that our vector field looks like that, with a saddle surface-like behavior. And let's again assume that we have a path that's sort of going in that direction. All right, let's assume that's C. So what this measures is, in some sense, the work done by a particular force that is going with or against it. So if you calculate the line integral over this particular path for this vector field, you're going to get a negative number because you're going against the flow of the path. And if we were to calculate the line integral of this vector field, say along this particular path, say C2, that's going to give you a positive number. And we have calculated before that if we do, for example, a circle, let's say counterclockwise or even clockwise, you're going to get 0, because in some sense in this particular field you have positive, that's going to be negative, that's going to be positive, that's going to be negative, and we have that symmetric nature of a saddle surface, so pretty much all those positive, negative line integrals will cancel each other out and give you a value of 0. All right, so that's some of the things that we've talked about before. So let's also do a couple other calculations. Keep in mind, let's just do another review topic. We say that f is a conservative vector field if there exists a function, f, sometimes called a potential function, that satisfies the gradient of f is equal to that vector field component. And sometimes we even call f a gradient vector field. So let's assume that we're working with a conservative vector field. And let's assume that we have some path C that's parametrized by some function u. So what is this going to be? So that means this is going to be equal to the integral from a to b with respect to t of the gradient of f, and keep in mind this is of x, y, and then we're going to replace x, y with u of t, and then we're going to dot product that with u prime of t dt, because that's what the differential of u is equal to. So what's the gradient of f equal to? Let's assume by definition that this is going to be equal to fx and then fy, and then that's going to be dot product with, and let's assume that u has functions x and y. Let's call it x prime of t and then y prime of t dt. Since these are two-dimensional vectors, we can take the dot product in the typical way. So we're going to have the integral from a to b, and then we're going to have the partial derivative of f with respect to x multiplied by the dx dt portion. So that's that term times that term, and then we're going to do the same for the second component. Then we're going to have the partial derivative of f with respect to y times the total derivative of y with respect to t, and then we have a dt located here. All right. What we have here is a total differential of t located on the outside, and it's located here and located here on those. So what I can do is I can distribute these components inwards, and this is going to simplify to the integral from a to b of the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times the total differential of y. And this expression inside of the brackets should look familiar to you because that's just the total differential of f. So we can write this as the integral from a to b of the total differential of f. And then what I can do is I can multiply top and bottom of this expression by a total differential of dt. And what we have here is that this will be equivalent to the integral from a to b of the derivative with respect to t of f of u of t dt. And let me just put this expression in brackets. And this should look familiar as the fundamental theorem of calculus because it's the integral of the derivative or the antiderivative of a derivative, which will just be equal to the functions evaluated at its endpoints. That means this will be equal to f of u of b minus f of u of a, and that's by the fundamental theorem of calculus that we've seen before. All right, so what have we just shown? So let's do a quick recap of that. So we have that the integral of the gradient of f with respect to u over some path c is equal to f of u of b minus f of u of a, and this is true if f, which is the gradient of little f, is conservative. Right? So that is, this expression can be re-represented as the integral along c of f du. So this gives us another way of evaluating line integrals of vector fields. Okay, so let's draw another vector field. Let's actually draw the same exact saddle surface from before. Let's assume we have this picture, this picture, this picture, and this picture. And before, keep in mind, we proved that this particular vector field was indeed conservative. That is, it does not have any rotational symmetry, i.e. the curl is equal to 0. So let's assume that we take 2 points. Let's assume we pick this point right here, A. Let's assume we pick this point here, B. And let's connect these 2 points, A and B, with some path. Let's assume that this is C1. And we could take the integral of this vector field, the line integral of this vector field along C1. And we can also evaluate this line integral over this path right here. And we can call it C2. Right? So if I calculate the line integral of f over C1, and let's assume U1 is the parametrization of C1, and we calculate the integral over C2 of f, and let's assume that U2 is a parametrization of that, this will be equal to one another because the endpoints are the same. Because as long as this vector field f is conservative, then the integral of it only depends on the endpoints of that path. And also the direction has to be the same as well, right? So therefore, this will be true if 1, f is conservative, 2, the endpoints are the same, and 3, the direction or the orientation of the parametrization, so the direction of the path, is also the same. Because remember, if you change direction, you'll get the opposite of what you get in the other direction. Okay? So let's assume, again, for the sake of conversation, that f of b, or u of a and u of b, will be equal to one another. So let's assume that u of a is equal to u of b. So if this is the case, and let's assume that f is still conservative, let's assume that we're integrating over some path c, and let's assume that this is a conservative vector field, and let's assume that u is a path, then that means this is going to be equal to f of u of b minus f of u of a. But u of a and u of b are both equal to another, so that's going to be equal to f of some number, let's say star, minus f of the same number star, and that's going to be equal to 0. So if we draw a particular path, and let's assume again that we're working over our conservative vector field, represented by that saddle surface, and let's assume that we have this path here. Right, so if that's our path particular c, and we integrate along this particular path, so if we calculate the integral of f along c, and since it's a closed path, you might see some people draw a little circle on that integral representing that it's a closed contour, then the integral of f du will be equal to 0. Consider these two contours, c1 and c2. Together, that forms what we call a closed loop. Some people also call it a closed contour. And let's also denote c to be equal to the union of c1 and c2. And also, let's assume that we have another path here, and let's assume it just goes in the opposite direction of c2. We can call that opposite of c2. You can call it c3 if you don't like the notation. Right? So how can we represent this particular diagram in terms of line integrals? And let's also assume that we're integrating over f, which is going to be a conservative vector field, potentially. Right? Actually, let's not make any assumptions yet. Okay, so then the integral over c of f du, this will be equal to the integral over c1 of f du1, let's say, plus the integral over c2 of f du2. Right? So we have that particular relation, and keep in mind, that's going to be true for any vector field f. It doesn't have to be conservative. Right? So let's assume that the integral over c of f du is equal to 0. This does potentially imply that f is a conservative vector field. Obviously, if f is conservative, then this holds. But if this is true, it's not necessarily true that f is conservative, right? So keep in mind that that is not a bidirectional statement, right? So just because the integral is equal to 0 doesn't mean we're working over a conservative vector field, right? For example, you can pick a point to construct of c that's always going to be equal to 0 regardless of the vector field you're working in. So if the line integral is equal to 0, then what kind of things can we get out of this? Well, that means that the integral over c1 of f plus the integral over c2 of f, this will be equal to 0 as well. Again, we're not assuming that we're working in a conservative vector field. So what is this going to mean? So that means that the integral over c1 of f will be equal to the opposite of the integral over c2 of f. And by properties of integrals, the opposite of the integral of c2 is just equal to the integral over the opposite of c2 of f. Right, so we have that the integral over c1 is the same as the integral over minus c2. So if we think back to our picture and what we had above, so here we have some point A and here we have some point B. So again, we're working over some vector field f, and we didn't assume that it is conservative. So if we have this particular path here, let's call it C3, and if we have some other path, let's use a different color, let's call this path over here C4, then if the line integral over the entire loop is equal to 0, then these integrals over c3 and c4 will be equal to each other. So the integral over c3 of f will be equal to the integral over c4 of f, where f is any vector field. And you should be able to verify that these statements are bidirectional as long as you are able to argue a couple subtle points in between. So with these things in mind, we can state the following very important theorem. And it says the following, that the integral over f du, where u is some parametrization of c, is independent of path. So I should be able to find this line integral regardless of the path I take, as long as the endpoints are the same, if and only if the integral over c of f du is equal to 0, and that has to be true for all closed paths c. And this value here, c, doesn't have to be the same exact path c. We can call that, for example, another path, gamma. All right, so let's just talk about this just for a moment, just to make sure we understand what this means. So if we have some vector field, right, so let's assume we have this vector field here. I don't know what this vector field looks like, and I don't want to. And let's assume that we want to calculate this particular line integral here. All right, let's assume that's our path gamma. There's a point A, there's a point B. And let's assume that this is the line integral of the vector field f that we're interested in evaluating. And you might be thinking, well, maybe that path is super complex. Can I just connect these 2 points with a line segment? Because that at least is a little bit more easier to parametrize, because we have to usually parametrize x and y with respect to some parametric function u of t. Right? So obviously, maybe I want to use this particular path, let's call it gamma 1, instead of the original gamma. Can I do that? Well, if I take that particular vector field f and dot product with an arbitrary parametrization u, where c is any closed path. For example, you can take any circle, any ellipse, any closed path whatsoever. So for example, if we were to take this path here and we get 0, that's a good sign. And if we take this particular path here and got 0, that's a good sign. And if we take this particular path here, was that equal to 0? Yes. Well, that's a good sign too. So if all of these closed paths are equal to 0, then it doesn't really matter what path you take. And keep in mind, this holds for any vector field, not just conservative. But we already know that if we're working in a conservative vector field, that the integral will be equal to 0. Therefore, all line integrals will be independent of path. Yes, it's a little bit more harder to prove that the integral over all closed paths is equal to 0 in order to justify that, yes, we are pretty much flexible on the path that we take as long as the endpoints are the same. But this is extremely useful when we were working in conservative vector fields. So that's the main point to take away here, at least for the time being. The next theorem brings back a statement that I made some time ago when we first were introduced to the idea of vector fields. So let's assume that f is a vector field with components little fxy and little gxy. And let's assume that it's conservative. That is, there exists some potential function, let's say h, such that the gradient of h is equal to f. Then, if this is true with these components f and g, then it satisfies this partial differential equation. Partial f with respect to y is equal to the partial derivative of g with respect to x. So if this is true, then this means that the partial derivative of f with respect to y minus the partial derivative of g with respect to x will be equal to 0. And keep in mind, we had already defined the two-dimensional curl of a vector field. So clearly, this is going to be true if and only if the two-dimensional curl of a vector field will be equal to 0. Of course, we'll leave the proof of this statement for you. It's a little bit more, I wouldn't say difficult, but I don't want to get into it, at least today. I think it's more appropriate for analysis audience, but that's up to you. So if this is the case, then what do we know? So that means if f is conservative, then the curl of f is equal to 0. Yes, this statement only covers the two-dimensional case, but it's also going to be true for the higher dimensional cases, such as 3-dimensional, 4-dimensional, 5-dimensional, which is going to motivate, in some sense, why we define curl like we do. Right? In some sense, we want this to be true, so we define curl in a special way such that it is satisfied. Right? So what other things can we build from all of these things that we have discussed up to this time, right? Because we have so many different theorems, so obviously they have to be interconnected some way, right? So let's assume that we have the expression fxy to be equal to fx and then g of x, y. And let's write this parametrization. Let's call it du or dr or whatever you want. Let's assume that du is equal to dx dy. Right? So once we have this, then the integral over some path c of f du will be equal to the integral over c of fxy gxy dot product with dx dy, and that's going to be equal to what? And then we can write that as dt if we want to, or we can write this, because this is another way of writing line integrals, the integral over c of fxy dx plus gxy dy. So we have this alternative representation for a line integral. And on the surface, you might be like, well, that seems a bit awkward. Like, why would I ever want to write it that way? Well, there are some advantages and disadvantages in the realm of applications. I'll talk about them later. But if you ever see something like, calculate the integral over some path c of, let's say, x squared y dx plus sine of x to the power of y dy. Right? So how would we evaluate this particular strange integral? Because it's not very often, at least from the single variable calculus word, where you have your dx here and a dy here, because usually we have an integral here and an integral there. But keep in mind, this is in some sense possibly an area integral in disguise. We have x and y. But according to this is the same as the integral over c of x squared y and the sine of x to the power of y dot product with dx and dy. So technically speaking, this is the vector field f that we were integrating, and this right here is your u prime vector that we have already known up to this point. So we can write this equivalently as the integral of x squared y sine of x to the power of y times, let's say, du, where u is the parametrization of the path. And then you would integrate this using whatever methods you have up to this point, right? But if you ever see something strange like that, you can always write it in this equivalent form. Just saying. Now, let's also look at these things from a different angle. Let's suppose that C is a closed contour or closed path, a closed path implying some bounded domain, let's call that bounded domain D. All right, so let's draw a little picture, see what we're talking about here. So here we have some closed contour. That's going to be our C. And then inside of it, we have our domain D. Right? So, question, is it possible to relate the area of the region, in particular D, with respect to, is it possible to relate the area of the region D with respect to the line integral over the path C that encloses that? This might seem like a far-fetched idea, but from single variable calculus, we've actually already done this. So remember that if we integrate from a to b of the antiderivative of f of x dx, this was equal to f of b minus f of a, right? And what does this integral calculate from a geometric standpoint? So if this is a and this is b, then this area, or this integral, calculates this region here, right? This calculates this area. But what does it exactly do? So this object this object, which is the area, is dependent on the boundary only. But this is a one-dimensional boundary, right? So we have this here and this here. Now we're enclosing it with a two-dimensional region, in this particular case C, and we want to know, are these things connected? The natural answer is yes, but the question is how? That's what the next statement I want to walk through discusses. The next theorem that I want to discuss is known as Green's theorem, which builds a beautiful connection between line integrals and double integrals, and it says the following. Suppose that C is a positively oriented, smooth, simple closed contour. Pretty much it means a closed loop that's smooth, differentiable, and so on. Let's assume that D is the region that's bounded by C, and let's assume that A is the area of D. Let's also assume that F and G have continuous partial derivatives in two-dimensional space, where F and G are the components of the vector field. Let's call it F. Then the integral of F, or the line integral over C of F du, where u is a parametrization of C. And keep in mind, this is also sometimes written as the integral of C of F dx plus G dy. And here I'm assuming that F is equal to little f, little g. Then we can actually find this, and this is the new part that Green gives us, can be found by doing the double integral over the two-dimensional region D of partial derivative of g with respect to x minus the partial derivative of f with respect to y dx dy, aka dA. Right, so this is what we refer to as Green's theorem. Right? And yes, the thing located right inside of that double integral is indeed the curl, and that's going to be very useful in just a moment. Let's just do a couple examples of how to use this. So let's calculate the line integral. Let's calculate the line integral of, let's choose vector field fxy is equal to y minus x over x squared plus y squared equals 1. You know, unit circle. So we're going to do this in two different ways because we already know how to evaluate line integrals. That's not new. But this gives us another way of evaluating line integrals with double integrals, which we also know how to do. So it gives us two different ways of solving the same exact problem. That is, it's two different problems with the same exact answer. All right, so if we approach this from the pure perspective of line integrals, then what we're going to be doing is letting u of t be equal to, so we need to parametrize this unit circle. That's very easy to do. We can let u of t be equal to cosine t sine t, where t belongs to 0 and 2 pi. And therefore u prime of t will be equal to minus sine of t and then cosine of t. So therefore, the integral over this path c of our vector field y minus x dot product with the derivative, which is going to be equal to, let's call it cosine t sine t derivative dt, is going to be equal to what? So this is going to be equal to the integral from 0 to 2 pi. So y is going to be equal to sine of t, and then x is going to be equal to cosine of t, which is going to turn into minus x. So this is going to turn into sine of t, and then cosine of t. And then we're going to have the derivative of our function. And what's that going to be? And let's not make any silly mistakes here. That's going to be minus cosine of t. And then the derivative is going to be equal to minus sine of t cosine of t dt. And then that's going to be equal to minus sine squared minus cosine squared, which is the same as minus sine squared plus cosine squared, which is going to be equal to minus 1. So we're going to have the integral from 0 to 2 pi of minus 1 dt, which we know is going to be equal to minus 2 pi. And if we were to rotate in the other direction, you should realize that that's going to give us the area of the circle. Let's see if we can get the same exact answer from the double integral approach that Green's theorem claims to give. Right? Now, no one said that this is the area of a circle, right? Yes, double integrals do give areas, right? But this is just the line integral of that vector field. So the integral of f du will be equal to the double integral d of the partial derivative with respect to x of g, which is minus x, minus the partial derivative with respect to y of f, which is y, with respect to a. All right? So since our path is the unit circle, we're going to look at it in the rectangular form, or you could do it from the polar form. It's really up to you. So that's minus 1 to 1, so we can go vertically or in polar coordinates. Let's do the rectangular first. So in the rectangular form, that's going to give us minus 1 to 1, and then the integral from minus the square root of 1 minus x squared to the positive square root of 1 minus x squared of minus 2 dy dx. And again, what is the minus 2? Well, that's going to be minus 1, which is going to be our minus 2. And then we can integrate this without any issues, or you can do it in polar form. It's really up to you. So this is going to be equal to, switch into polar form, so r is equal to x squared plus y squared, x is equal to r cosine theta, y is equal to r sine theta, and this is going to be equal to minus 2 multiplied by the integral from 0 to 1 for the radius, and the integral from 0 to 2 pi for the angle of r dr d theta, coming from the Jacobian dx dy. All right, so this is quite easy to do. So this is going to be equal to, so notice that there's no theta here, so I can write this as minus 4 pi times the integral from 0 to 1 of r dr, and that's going to be equal to minus 4 pi times 1/2 times r squared, which is going to go from 1 to 0, and that's going to give us our minus 2 pi answer. Right? So notice that they do give us the same exact answer. So now it's really up to you to answer the question, which method is easier? To evaluate line integrals via parametrization, or to evaluate line integrals via double integrals? The choice really comes down to you and what you're good at. So another question we can ask is the following. Does Green's theorem give us anything really new to the story? Because on the surface you might be thinking, well, I don't really care. I already knew how to find line integrals before. Why do I need another method to do it outside of convenience on occasions? Right? So what does Green's theorem allow us to do so far? Well, it allows us to find line integrals with the domain and that area without actually having to know what that area is. So another question is, well, what if we want to know what that area is? Because currently, without numerical approximations for an arbitrary weird region, if that parametrization U is very strange, finding that area might be extremely difficult analytically. Right? So what do we know? So what we would like, at least from the Green's theorem, is to get the area of that region. Well, keep in mind, the Green's theorem states that this partial g partial x minus partial f partial y dA is equal to the integral over some path c of f times du. But the only thing in this story that we really care about now is how to solve this equation for a. Well, if this part was identically equal to 1, then the double integral over any region D of 1 dA will just be equal to a, right? So all we would really need to do is to find some function f and g that satisfies this partial differential equation that gives us that particular area a, right? So it's actually quite easy to generate a. We just need an f and g that makes this true, right? So we would like that partial g, partial x minus partial f, partial y is equal to 1 in order to solve this particular equation. So what vector field has a curl of 1? Right? So there's infinitely many vector fields with a curl of 1. So this gives us a couple options for calculating area. Some will give you answers a little bit more easier than others. But what we can do is we can choose, for simplicity, fxy to be equal to 0 and gxy to be equal to x. Right? So if you choose these particular functions f and g, you will realize that both of them make this true. Right? So that gives us a beginning starting position for evaluating the area of some region. Right? So that means a, which again is the double integral over some region D of partial g, partial x, minus partial f, partial y, of dA will be equal to the integral over c of f dx plus g dy, and this, by choice of our f and our g, will be equal to the integral over c of 0 dx plus x dy. And this simplifies to a very, very basic integral. A can be found by doing a closed contour, because keep in mind this can be chosen to be a closed contour if you want, over f x dy. Right, so this is another way of writing area. Right? Very basic, very simple. Let's see if we can actually find the area of a shape that everyone already knows. Right? In particular, the area of a circle. And let's assume that this is an arbitrary circle of radius r centered at the origin. Right? So generally speaking, what will we like? Well, we would like a area of a region for which we can parametrize. Right? So how do you parametrize a circle? So x is going to be equal to r cosine t, and y will be equal to r times the sine of t, and t is going to range from 0 to 2 pi. So that's the parametrization of our curve. Right? So what is dy? Well, dy, because we need to figure out what this integral is, dy will be equal to r cosine of t dt. All right? So therefore, the area of our region will be equal to the closed contour integral over our path c, and let's assume that's positively oriented, and it indeed is smooth, of x dy. This will be equal to the integral from 0 to 2 pi, because this is still a line integral over a vector field, of r cosine of t times dy, which is going to be r times cosine of t dt. All right. So once we have this, what can we do? So this is going to be equal to r squared times the integral from 0 to 2 pi of cosine of square root of t dt. And now we can use some double angle identity tricks here in order to evaluate this, but there's a couple varieties you could go. But this is going to be r squared divided by 2 times the integral from 0 to 2 pi, then 1 plus cosine of 2t dt. And this is just some trig identities from before, in case you don't know that. And then we can integrate each of those pieces one at a time, and this is going to give us what? So it's going to be r squared over 2 times the integral from 0 to 2 pi of 1 dt, and then the integral from 0 to 2 pi of cosine of 2t dt. Keep in mind, cosine of 2t is a periodic function with period 2 pi divided by 2, so it actually repeats twice over the interval 0 to 2 pi, and therefore it's going to cancel itself out in terms of area, so that's going to be equal to 0. And then we're just going to be equal to the integral from 0 to 2 pi of 1, which is going to be equal to 2 pi. The 2's are going to cancel out, and that's just going to give us pi r squared, which we already know to be the area of a circle. Right? So this formula definitely does work for finding areas of regions, as long as we know the parametrization of it. Now, this example is super easy. Let's actually work through something a little bit more computationally intensive and possibly has a formula that you might not already know the answer to. Let's consider this particular parametrization, the sine of t over 1 plus cosine squared of t, and then we have sine t multiplied by cosine t over 1 plus cosine squared of t, where t ranges from 0 to 2 pi. If you don't know the graph of this particular shape, it has this figure 8 type of geometry, and it's symmetric about the vertical and the horizontal axis, in case my rough sketch doesn't demonstrate that. So our question is, what is the area of the area bounded by these particular curves? Due to symmetry, it's possible that we want to find the area of this region and multiply it by 2, or the area of this region and multiply it by 2, or we can attempt to find the area over both at the same exact time. Let's see what our double integral or line integral Green's theorem connection gives us. So what is our area going to be equal to? Question mark. So this is going to be equal to the integral over c of x dy. This is always going to be true, right? So keep in mind, this is going to be x, this is going to be y, and you need to differentiate y with respect to t. So that's going to be a little messy, so let me do all that work for you. So that's going to be equal to the integral from 0 to 2 pi. Then we're going to have our x, which is going to be the sine of t, all over 1 plus cosine squared of t, multiplied by, and then we have to do some quotient rule. So 1 plus cosine squared of t times minus sine squared t plus cosine squared of t, then minus sine t cosine t times minus 2 cosine t sine of t, all over 1 plus cosine squared of t squared dt. All right, so once we have that, then we have a couple 1 plus cosine squared t's on the bottom, so we can combine them if we want to. On the top, we're going to have our sine t all over 1 plus cosine squared of t to the power of 3 times, and then once we simplify and FOIL the top, what is that going to give us? Let's see, that's going to be 2 sine squared t cosine squared t, and then we're going to have a minus sine squared t plus a cosine squared of t minus sine squared t cosine squared t, and then plus a cosine to the 4th of t, all over 1 since we factored out the rest of it out. And then what is this going to be? So this will be equal to, so a is equal to, let's do a different color just to color things up a bit. So a is equal to the integral from 0 to 2 pi of sine of t all over 1 plus cosine squared of t to the power of 3. Pay attention that sine here is going to be an odd function and the bottom is going to be an even function, multiplied by cosine to the power of 4 t even, cosine squared of t even, sine squared of t even, plus sine squared t cosine squared t even. So odd times even, odd, that would be 0. Right? So you might be thinking, well, the area can't be 0, can it? Well, keep in mind, this is the line integral of the vector field. And from some of the results that we described before, for example, if we talk about this particular path here, and this particular path here, notice that the direction that these paths are going are opposites of each other, right? This integral is going in that direction, and this integral is going in that direction. And Green's theorem technically only applies to your positively oriented integrals. So all you would have to do is mirror this and then add them, or just find the one on the left-hand side and multiply it by 2. Right? So from this particular picture, you should be able to verify that if this is c1 and this is c2, then the integral of c1 of our particular function, let's call it u, will be equal to the minus integral of c2 of u. All right? So I leave it to you to verify one of these little pieces. All you have to do is just change your integral bounds, that the integral over c1 of u, this will actually be equal to just 1/2. Right? So that means that the true area will be equal to 2 times 1/2, because if that's equal to 1, that's equal to 1, and that's going to be equal to just 1. Right? Well, that's equal to 1/2, and that's equal to 1/2. Right? And that's going to give us our total area. Right? But that integral, quite a little bit messy, but definitely a fun integral in case you ever get bored. Now, these are some of the results for line integrals and line integrals of vector fields, and also double integrals and Green's theorem, how it connects those. Very, very powerful. We'll look at several other examples and applications in the future, but for now that's just an introduction to these very important integral techniques in vector calculus. Hope you enjoyed this video, and I'll see you in the next one. Take care.